Yes, so hi everyone. Please welcome Professor Hyun from Chung University, who will be talking to us about Higgs before inflation.
Okay, thank you very much for your being here to listen to my work seminar. This is based on this series of my papers published this year related to Higgs pole inflation. So basically, I will give you, this is the outline of my talk. I will give you an introduction, brief introduction to motivation of my work and the pole inflation in particular, realizing slow law inflation. And in the particle physics context, I would like to illustrate some working examples for pole inflation in particle physics point of view. And recently, because of this ACT, Atacama Cosmology Telescope result, we revisited pole inflation predictions for inflation and consider some corrections, loop correction to the inflaton potential. And the pole inflation is based on a particular form of the Lagrangian. So I would like to convince you that the pole inflation can be embedded in a more complete UV theory. Then I will conclude. So I think the cosmic inflation, there is no further explanation, motivation for cosmic inflation, can solve the various problems in the standard Big Bang cosmologies, in the standard Big Bang cosmology, such as horizon homogeneity, isotropy, flatness, and Rayleigh problems in the grand unified theories or extended symmetries. And we know that the observed cosmic microwave background is homogeneous and isotropic in large distances. So we don't have a good understanding of the correlation between temperatures in the different regions in space. The slow law inflation has been introduced in terms of the scalar field in Platon that drives inflation and also reheat the universe. And the quantum fluctuation of the in Platon also generate CMB anisotropies that observe in the sky, and also can provide seeds for the galaxies and clusters, and also the inflaton could convert it to dark matter. So there might be some another role of the inflaton to make this the CDM standard Big Bang cosmology making more sense. So the inflaton potential can be shown in this form, and it start rolling in a sufficiently flat potential, and during the fuzzy digital background, during inflation, we can achieve sufficiently large expansion of the universe in such a way that the perturbations generated during inflation within the horizon during inflation, connection maybe.
Yeah, maybe the connection.
The perturbation generated during the inflation within the horizon can exit the horizon at some point in the later time of the universe, and to make the temperatures observed in the sky can be correlated once within the horizon in the past. So we can explain this almost homogeneous and isotropic universe based on this inflation paradigm. So recently, as compared to Planck result, the ACT announced their result, and they improved CMB measurement at a small scales. And if you combine the Planck together with the ACT, and sometimes with the BAO, baryon acoustic oscillation data from DAISY, you could show some significant deviation from what would get from Planck only in the spectral tilt, spectral index. In other words, so the spectral index parameterizes the scale dependence of the power spectrum, and this NS can be deviated from 1 and slightly smaller or greater than 1, depending on this slower parameters epsilon and eta, which are determined by the derivative of the inflaton potentials. So since observed value of the spectral index is close to 1, which means the almost scale invariant power spectrum, we need to rely on slower inflation to explain the data. And the tensor to scalar ratio, the tensor contribution to the cosmic microwave background anisotropies can be parameterized in terms of the tensor to scalar ratio R, which depends on the slower parameter epsilon. There is no observation for the tensor perturbation yet. Instead, there's a upper bound on the this R parameter, which is about 0.035 according to Planck combined with other data. So my motivation for recent ones, sorry, I don't know why.
Maybe is your thing going dead because you're on some power saver mode, perhaps?
Okay.
That could be
Also an issue. I think if I could.
Because I don't have a power.
Yeah.
I need to.
maybe if you just change your power settings.
Lower power.
Yeah, it's already on number.
Always they are only on the 3 power. Maybe I can put this. I forgot to bring my
Does someone have a
Power.
charger?
charger. Okay.
Okay, we'll just see if it keeps going down.
Okay, so then if you compare these two values, the one combined with ACT shows slightly larger value of spectral tilt. We need a more red tilt in order to be consistent with ACT result.
Lesser tip, because it's more close to the flat one. And it was one is flat.
Flat, yeah, flat.
Red tilt deviation.
Deviation from 1, okay, yeah, sorry.
So here is less deviation. Second thing actually, which I want to say is that if you will take just a atomic cosmology telescope, you will get precisely the same result up to the last 4 numbers. In the spectrum, you got also will be like 0.96, maybe 4, 5, or whatsoever, separate. And the whole thing, like 973 is coming from astrophysics, from DAISY.
Yeah, this.
You see, so it's very dirty result. But even in this case, there is a lot of systematics there, as you know very well. But even in this case, deviation between two things is 2 sigma.
2 sigma, okay, 2 sigma also. Yeah, I don't.
No, it's not very serious thing.
Yeah, it's not.
Sigma, as you know,
Yeah.
in any case.
Yeah.
But one has to understand also that Atacama itself give you precisely Planck value.
Okay.
Precisely Planck value. After that, they combine the things, they get 0.97 by God knows what, because they try multi-parameter game, and then they add on the top of it dirty astrophysics.
Yeah.
You understand that actually this
It
LB is not very clean stuff.
It could possibly be
skin stable. Screen stable. Maybe screen stable.
Yeah, we put it stable.
Maybe screen stable. And I don't know which one. Displays.
Perhaps advanced, or if you do scalars,
Sorry, display.
maybe advanced.
This
Maybe
one?
displays. Oh, yeah. Displays.
Display.
Yeah, I don't have a Mac, but maybe it's under some advanced option. Never mind. It's not this. It could. Maybe if we don't use this, it might somehow help.
Okay.
Yeah, why don't we just, do you mind using the normal pointer?
Yeah, sure. Okay.
I'll just remove this.
Sorry. Thank you for your comment. I think that this value is kind of exaggerated because of this DESI combined DESI result. It's combined. Without DESI, Planck ACT
Why
only.
it's called LB?
Okay, there is.
Why this is called LB?
I don't have an idea.
But it's lazy, right?
DESI DDR, I don't know, they have two sets of data. So one set of data, DDR1. If you combine another data set, the deviation is more dramatic. But this is a medium value that I'm shooting. But this kind of motivation, but we want to see some deviation from standard, I don't know, previously known inflation models. But I think the deviation is not dramatic yet, but yeah. So Stravinsky model that you might be familiar with is based on this simple extension of Einstein gravity with R square, and the coefficient of R square psi can be written as a non-minimum coupling for the dual scalar field phi. And you can show that these two Lagrangians are equivalent after integrating out the scalar field phi in the dual side. And if you take the Lagrangian in the dual scalar tensor theory and change the frame of the metric tensor to the Einstein frame, where the effective Planck mass becomes field independent canonical frame, then the potential for the scalar field is constant plus small fraction for large field values. So of course the this psi very simple extension of the Einstein gravity with one parameter. If you choose this psi or the coefficient of R square to be a certain value, then you can explain the observed CMB anisotropies. But you need to rely on very large value psi, 10 to the fourth, to be consistent with the Planck data. But I'm actually in this language, you need very large coupling. But there's another way of
C is dimensionless.
Yeah, because it's dimensionless.
So Newton's constant is in front of R over 2.
There's a Newton constant in front of R.
Is it? So you drop that. So
Yes.
never mind.
So there must be Planck to the fourth in the potential if you introduce Planck scale. So I think there are many ingredients in my talk, so I don't know if I can finish my talk on time. Hopefully, I can tell you more. The pole inflation is another realization of constant plus small fraction. The form of potential is almost the same as in the Sarbansky equation model. But in this case, it's not, there is no idea, but there's a real single scalar field sigma with a component, which is component coupled to gravity with a component coupling. They are 1/6, -1/6. And the potential form takes particular form in this way. This component factor square will appear in the Jordan frame potential. And that's just because of when you change the frame, you are canceling these factors to make the potential to be flat enough. But the idea is that if you change the frame from Jordan to Einstein frame, then the scalar field sigma has a non-canonical kinetic term, and kinetic term becomes singular near the pole of the kinetic term, where the inflation is taking place. So in the Jordan frame language, the potential looks like this. There are two minima, 0 and non-zero value of sigma. But if you go to the Jordan Einstein frame, then the field is kind of extended such that there's a large field range over which inflation could take place.
Could you maybe tell what is the reason for these guys who play with elementary functions? Okay, just making one substitution instead of the other one. Why won't you just start with the final tangent hyperbolic potential? Or there is justification of this wall potential or whatsoever, or this unusual coupling with gravity, or there is nothing like this one. Otherwise, it looks like, okay, elementary exercise in the maybe 9th grade of primary school.
Yeah. Sure. Why things make things more complicated. But, yeah.
Okay.
Yeah.
Is there any kind of blah 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 justification for?
Yeah, I will tell you more about this. I spent hard time to get around why this is so. Okay, so and I come up with answer to that question, hopefully. So, and of course, we need reheating period after inflation because the temperature of the universe is almost zero during inflation, and we know that the period of reheating is not instantaneous. Normally, if inflaton doesn't couple strongly to the other factors. So therefore, number folding that we are considering to solve the following problem depends on the period of reheating. There is matching between inflation and post-inflation or standard Big Bang period. So then there's an additional contribution. If reheating is not instantaneous, it depends on the equation of state during reheating and the reheating temperature at the end of reheating. So this shows that depending on the equation of state during reheating, can see that number folding as a function of reheating temperature. So number folding can be between 20 or and 20 and 70, depending on the equation of state and the reheating temperature. But normally, if you make an assumption of instantaneous reheating, then the ballpark value of the number folding is about 60 or 50. So people normally are ignoring the uncertainty coming from reheating period in the calculation of number folding. And if you know the number folding, then then this spectral field and the tensor to scalar ratio depends on the number of folding. So therefore, if you don't know the reheating period where there is irreducible uncertainty in your prediction for inflation.
But in your case, you are using Higgs fields, right? So,
Yes.
So the coupling, the impact of coupling to the standard model is fixed, right? So why can't you just do the numerical estimate?
Yeah, then you can, in principle, yeah, you can calculate. I think we didn't do a full analysis of reheating. I will show you some slide on the estimation of reheating temperature, but I didn't put the number for the number of folding, but you will have an idea how does reheating, how do we determine the number of folding when the reheating dynamics is known. And then another maybe interesting aspect of inflation is that normally we don't include quantum corrections to the inflaton potential by assuming that the quantum corrections are so small. But here, in particular, in the pole inflation or any Higgs-like inflation where inflation depends on the quartic potential. Here, for instance, if n equal to 4, we have a dimensionless coupling, which run as a function of renormalization scale or Higgs field values. So then if you consider one loop or two loop running of the Higgs quartic coupling, you will see the dependence of the quartic coupling on the inflaton field values. And if you consider these corrections, they will change the shape of the potential during the reheating period. Then you will make a modification in your prediction. So another aspect is the pole inflation in particular relies on a particular form of the functions. Here, this frame function and the potential. So in particular, component coupling is based on the component symmetry. And also we know that the Higgs potential almost vanishes at high scales. As you can see from the running Higgs coupling, as you go to high energies, quartic coupling tends to vanish at high scale, hinting at conformal symmetry or biosymmetry. The conformal symmetry is nothing but the rescaling of the four-dimensional coordinates. And this alpha scaling parameter could be global or local. So in our case, we took this alpha parameter to be local and gauging the conformal symmetry. And then we need to introduce gauge version associated with this new gauge symmetry called photon. So in addition to the conformal symmetry, the conformal symmetry will determine the form of the nominal coupling of the scalar field to gravity, and also the form of the particular form of the frame function depends on the unbroken isometry in the field space. So here, this chi is dilaton and sigma is inflaton, and chi square minus sigma square is invariant under the symmetry transformations. So this is for SO1, non-compact isometry in the field space and containing dilaton. And if you generalize the situation to the multiple field, such as in a Higgs field or in Peccei-Quinn field, you only have to extend this non-compact symmetry to SO1 combined, so that the non-minimal coupling for the scalar field respect this isometry in the kinetic terms. So there are the kinetic term with the co-derivatives, etc. So
This A here?
so A is a free parameter. So here I chose A in such a way that the kinetic term takes the canonical form in this way. So there's A and
So D mu and del mu are different?
yeah, this round mu is a usual derivative, and D mu is a covariant derivative for the biosymmetry. The Y gauge field is included. So I will tell you more about this. Just
One of the kinetic energy is negative.
yeah, one of the kinetic energy is negative. So dilaton, if you take the normal sign kinetic term for the Higgs field, the dilaton has the opposite sign of the kinetic. But there is no problem because this sigma, in the end of the day, is eaten by the gauge field, by gauge field. It's not a propagating field freedom in the unitary gauge. So do you have
One of the sigma post.
in usual sense, this comes with a wrong sign kinetic term. In that sense, it looks ghost, but chi this would be the longitudinal part of the Y gauge field, and you can choose the gauge such that the chi field is eaten by the Y gauge field. There is no problem.
Anyway, one of chi and sigma has a wrong sign, the kinetic term, but it does not make any problem.
But there is no problem, so I will show you.
And what is d capital there? Why you separate d capital covariant derivative from the normal derivative?
I think this is
Because continuation of the line, right? It's not it.
so. This is most general.
No. It's more general.
Yeah,
Just, it's not actual continuation of the previous Lagrange.
Generalized this first line plus second line.
Second line is
Second line.
generalization of the first line. Or
I mean, I think it's confusing because you have
Relax.
kinetic term of chi and sigma in the first line, and what looks like kinetic term of chi and sigma in the second line, but with different derivatives. So that's a little bit odd combination.
I think this chi square r plus normal kinetic term itself by the million, and sigma square r
Oh, I see.
plus
The first line is
The normal
by million
derivative.
by itself.
by the million itself, and this covariant derivative term is by the million itself.
wait a minute, but first line and second line is continuation or it's just the same thing rewritten as
No, he's adding additional term, which is by invariant and preserve the by invariance.
and then why actually there comes the capital?
Because
Instead
chi
of- no,
transform on the by transformation,
This
and he's inventing the gauge field for that transformation. He's gauging by transformation.
But using in high with normal derivative, and then add also a with this covariant derivative.
so this is a normal because
This I understand, but
It's
when
a
you would
minor
combine, for instance, this thing with d capital mu high.
Yeah.
Because you cannot even say anything about sign from the d mu high story.
sure.
The question about what.
This A can be arbitrary parameter. A is arbitrary parameter in this up to here. There is no preferred value of A. It's just I'm adding. But if you take the combination of this normal derivative and covariant derivative terms, then this this Lagrangian is chosen in such a way that the Higgs kinetic term is has a
Okay.
correct sign. Okay. So Higgs boson inflation, I think. So I think that in the previous discussion, I consider only singly scalar field, but Higgs contains more than one field, the Higgs doublet. So it is more it looks more complicated. But just it can be generalized in a simple manner, and we choose the unitary gauge for the Higgs field, then we can show that resulting Einstein Lagrangian takes the same form as before, where single field appears, only single field appears.
So when you say Higgs, you really mean electron Higgs.
Yes, standard Higgs. So
But how Paul appears if it's
the pole appears because of Higgs couples to gravity conformally, and this the pole position is where the frame function vanishes.
so then after that why you wouldn't normalize canonical?
Yeah, we are going to normalize the connected term. Yeah.
No, it's not canonical.
No, canonical for the gravity.
For the gravity, yes, but after that H you can.
H is not canonical form yet.
Or you're asking why not make a field definition of small
Of
H
course.
to make it canonical? Maybe because you want to look at things at the pole, right?
Yes, I didn't do anything here. I think I started from Jordan frame where Higgs kinetic term is canonical, and just the standard Lagrangian is added at this
Why does it
level.
have to couple conformally? Is it assumption or is it something? Why do we have to start with conformal coupling of Higgs to the gravity?
I thought that conformal symmetry is nice.
Do you like it? That's good enough.
The white pole is interesting.
I think that it's another interpretation of kind of fluoral region in terms of pole instead of large field values. So just to compare mapping between the two pictures, I
But the
think.
position of the pole correspond to the Planckian value of the field, right?
Yes,
The Planckian value of the field.
yeah, Planckian.
But where inflation finally starts, if you make redefinition, normal redefinition for the kinetic term of H small, what kind of potential you get? You get this tangent hyperbolic potential?
Yes, this is what
Okay, so this is
would get as. So canonically normalized kinetic term,
Okay.
we are ending up with the hyperbolic tangent form of the potential.
So now you tell us the tangent hyperbolic appears naturally from conformal symmetry, from Weyl symmetry. What you say.
Yes. Okay, so of course it can be more than Higgs potential. I assume the monomial type of Higgs potential, although we know Higgs quartic potential is needed for electroweak symmetry breaking. Just I want to
With the
be,
Jordan frame, you chose some the specific omega squared.
yeah.
So what if I take omega 3 or omega 1?
The power
Yeah,
of
does
this
it change?
exponent. It will change. Yes.
So the choice of this is just to make the potential flat,
Yes.
This value of NS you derive at the end of the day,
Yes.
that has nothing to do with the fact this is Higgs. It could be some other scalar field that's conformal.
Sure. Yes. But the running knows the coupling runs differently depending on whether it is Higgs or something else.
Which one?
Running of the, so if m equal to 2, the coefficient of this term is a dimensionless quartic coupling.
Coefficient anyway is a free parameter of the theory, right? It just tells you the amplitude of perturbation. What it has to do with the measurable, it's observable.
So I will tell you more about this. How can be matched to the observable coupling. But here until now, I think that I want to be more general. Monomial type, 1 by 1. How can we constrain them 1 by 1? But just to, I think if we start, I think that for Higgs field, Higgs mass is too small to be relevant for inflation. And the vacuum energy, to avoid vacuum energy at a later time, called graceful exit problem, we set the constant term to 0. And we need to start with the quartic potential or higher than quartic potential. And if you take only a quartic potential, then the coefficient of the quartic term to be 10 to the minus 11 to match the CMB anisotropy.
But wait a minute, but this is Higgs coupling constant, lambda 5, right?
Yes,
But we know this lambda.
yes,
From
we
the
know.
Higgs mass, and it has nothing to do with the
Of course, we need to understand why the quartic coupling is so small during inflation. But this value might be different from the one that we observe in the low energy.
So of 1 to be, right? So how can you get 10 minus 11?
You need the running. So,
No, but not up to such extent, because it can be because only logarithmically, right? Mass.
yeah, I will show you more. I will show you more. I will show you more how to get this value.
So in the standard model, lambda h becomes 0 at high energy, right?
Yes.
So which scale is it?
So in the standard model, normally 10 to the 10 or 10 to the 11 GeV.
So you have to postpone it to 10 to 9.
Yeah, we need to postpone it until Planck scale. We need to go beyond the standard to make the quartic coupling remain productive and small all the way to the inflation scale. So we want to delay the vanishing quartic coupling to a higher field values. That is the assumption, but I will tell you how to achieve it by the extension.
Right, but if you will take into account even two contributions, some resummation with the Higgs effective potential, then it's unbounded from below, as you know very well, at very high energies. Because it looks like actually it gets maximum at the energies 10.9 or 10.10 GeV, I do not know. But this is not one loop. One loop actually
Two loops.
is much low maximum. And after that it turns the side. Lambda, correct?
Yes.
Then, if the potential is unbounded from below, if it's like this one, of course, probability of tunneling is very small. It's like, okay, you have to wait about 600 years for the decay in this case. But nevertheless, how you can use this thing now for inflation, you assume?
Of course, I didn't say anything. I need to tell you more about how to achieve this value. I can say now, within the standard model, it is non-trivial to achieve this value because we need to tune the couplings within the standard model. But of course, we can rely on the uncertainty, the experimental uncertainty in the top Yuval coupling. So, but that's
it's not enough really, because we were looking actually at this potential. Some people claim that it can take second minimum as the values of field 1032 GeV, so complete psychiatric clinic, yeah. But the question is, for instance, when Шапошников and Безруков suggested this model, did they think about this kind of coupling constant, which is one loop or two modifiers?
I think that they look at this, and I think if you make Tarkov UR coupling to be small enough within the uncertainty of the Tarkov mass measurement, then you can achieve the quartic coupling to be positive, small enough, around all the way to the Planck scale. But I think we need to choose very specific value of the Tarkov UR coupling. Instead, you can think of the extension of the standard model. Okay, so I think that maybe you are more interested in how to get those potential, how to get necessary value of the quartic coupling. So maybe I will explain about that. So the rating dynamics, I think that since we know the couplings of the standard model Higgs to the standard model particles, we can rely on the perturbative reheating of the from the Platon couplings. So here, I think we computed the rating temperature as we change the power of the Higgs potential. And here, I think the realistic value, realistic situation, we need to see the rating temperature from this m equal to 2 cases. So 10 to the 9 or around 10 to the 8 GeV, if you rely on the perturbative reheating. But this is because of the Pauli blocking of the Higgs decay into heavy particles. Then we need to see whether heating effect is important or not. So this topic is under is a work in progress.
Sorry, so I know that in the critical Higgs simulation, there have been many studies about reheating and preheating. So what is essentially different?
I think the critical Higgs inflation need conformal coupling, not conformal coupling, non-minimal coupling to be different from the conformal coupling, and so about 10 or 100 ish value for the non-minimal coupling, and the quartic coupling is around 10 to minus 6 or so. So it's a different region of the parameter space. If you make this more general, yeah.
You should never write favor to explain Atacama cosmology telescope. Atacama cosmology telescope by itself contradicts nothing. It just precisely gives the same parameters as Planck. Vice versa evidence.
Okay.
You see?
Okay.
Therefore, it's unfair to say that okay, Atacama cosmology telescope is something.
Okay.
You see?
I need to be more careful about this statement.
No, but it's really the case.
So I will put some more sentences here. If we believe ACT,
yeah, I discussed
we need
this.
this. Okay.
0.973. I told him, come on, look, open your eyes and look what Atacama cosmology telescope is. The same, precisely the same spectral index as Planck. I tell you, all junk comes from astrophysics.
Okay.
Well, we can run over an hour, of course, but just in the interest of time, maybe we can wait until after the presentation and then ask a lot of questions. Because it's running kind of late.
Okay.
Yeah, but take your time. We can go over it.
Okay. I think I should have. I should speed up a little bit.
Yeah, just.
Or you can skip.
Or you can skip.
Okay, I can skip. Okay. better way to
But I mean,
speed
talk
up.
about anything important. We could go over an hour, just, we don't want to drag on.
Okay, I will, I think this is one, I think I need to spend 1 hour to explain everything about this PQ realization. So let me skip, although they are very interesting. So loop correction. So Higgs pole inflation in itself relies on a particular form of the potential and the coupling to gravity. So as usual, Higgs couples to the standard model particles, you can consider one loop or higher loop corrections based on Goldman-Weyl. So we only have to identify the effective masses for the standard model particles, and also we are adding a single scalar field to have more freedom. So this, as a consequence, this is the expansion of the Higgs field below Planck scale. And the quartic term and the sextet and higher order couplings required because compound coupling from the beginning and also higher order potential in the Jordan frame potential, those are non-renormalizable. Therefore, theory is not renormalizable, but we can truncate the expansion of the scalar field, Higgs field, of a certain order to make sense of this expansion, and keep this quartic coupling to be dominant after renormalization. And we want to see how this quartic coupling runs at high energy scales, whether this can be small enough. So then we consider the running coupling with standard model, like in the sense the beta function coefficients is always negative, even if you add extra scalar field. So here left-hand side here, the singly scalar threshold pops up at some point here. I choose the singly scalar mass about 10 to 9 GeV. Then the quartic coupling receives threshold correction. There's a jump in the quartic coupling and run again due to the renormalization equation with the extra term coming from the singlet coupling. So then there's a two effect combined to make this quartic coupling to be positive and small all the way to the front. Okay? And here the beta function remains negative because of that. I call that this running behavior is a standard like. So the message is that the quartic coupling, both quartic coupling and beta function, almost zero near the Planck scale, and this statement is true at two loop orders, two loops, standard model two loops, singlet two loops.
So you don't have hierarchy problem?
There's a hierarchy problem.
I mean, Higgs, the quadratic tables.
Yes, yeah, we don't have an understanding on the. Of course,
that needs to be solved.
So this, of course, the singlet scalar mass is pre-Fermi.
I mean, since you chose 10 to.
This is particular value. I want this scalar field to be related to the PQ violation. So this why I choose 10 to 9, but it can be smaller than that. So I said the vacuum instability scale in the standard model is about 10 to 10 or 10 to 11 GeV. So therefore, new particle must be below that scale. 10 to 9 GeV might be still okay. 10 to 8 or 1 TeV, there's no problem. So another case is that you cannot see visibly, but if you take it a closer look at the running coupling and the beta function, in this case, there is a turning over behavior of the quartic coupling. There is a minimum value of the quartic coupling appearing, and the beta function becomes positive. The sign changes as you go to higher field values. So this is called the case with the scalar singlet domination. And the PQ pole inflation also we can do, but in this case, PQ pole inflation is the radial component of the PQ field, and the PQ field is extra field, and we have a freedom to choose for the PQ field couplings. So we only have to take small values of the extra couplings. There's no problem. So just the Higgs inflation, there's the constraint. So as I said before, we took the running coupling of the two loop orders after canonically normalizing the kinetic term for the photon. We have a power fractions, linear and quadratics, in the coefficient of this hyperbolic tangent form. So then we found that the loop fraction shift spectral index and the tensor to scalar ratios in terms of this beta function, one loop and two loop beta function coefficients. What is dominating is the one loop beta function coefficients. If one loop beta function coefficient is positive, we can make spectral index to be larger than the one in the pole inflation. Is to be more consistent with this dirty astrophysics data. So there are two cases when the one loop beta function is positive. The one loops are sufficient to make this more consistent with the ACT. If the one loop beta function is negative, the two loop contributions are equally important. Just this is parameter space for one loop and two loop beta function coefficients. So for the rest minute, I think I will tell you how to make sense of this construction for inflation. Actually, I come up with this idea, and I finished this paper in a week. It's a very short paper, and unfortunately, the paper was published in PRL. And there is the PRL reference in this time, so generous. So just I only have to update some part. So it was, I was very lucky. Maybe, I don't know. So in any case, this Higgs and Weyl symmetry that I mentioned before, motivated by the vanishing quartic coupling in the UV, and the compound symmetry or Weyl symmetry can be gauged by introducing gauge field by photon. This Lagrangian is the same as before, but I can add more than that here. And this, the Weyl gravity, we are adding global isometry, which is the global symmetry doesn't have to be exact. So we can violate the global symmetry. But this it is nice to start with the exact global symmetry in the beginning and to make sense of the resulting form of the Lagrangian. So the form of the Lagrangian is that except this f function, the coefficient of the quartic potential, if you impose the invariance of chi square minus sigma square, the potential will take this form together, which are invariant under the Weyl gauge symmetry and this non-compact isometry. So then you can see the connection between the coefficient of R to the particular form of the potential. So you don't put 3 here or 1, okay, because of the comparison. Then the coefficient of this term doesn't have to respect the full isometry. So this SO 1,1 isometry can be broken, but it can therefore but nonetheless, we want to keep the conformal symmetry exact because it is gauge symmetry. So this the form of the coefficient must be the function of the ratio of the field. The Higgs field divided by dilaton. And then this chi is there's a flat direction along the chi. Chi is the dilaton. It would be Goldstone mode. So the flat direction. So we can choose certain gauge. Any gauge is possible, but we choose convenient gauge choice. Sorry. Okay. So, and to determine the Newton constant from the vacuum expectation value of dilaton, and the Weyl photon mass accordingly are generated. And this additional term, the covariant derivatives, generate a non-zero mass for the Weyl photon. So
could you, sorry, I'm not supposed to ask a question.
Oh, we're almost
there.
or maybe just right after.
So, okay, so in this Lagrangian, in this approach, there's a parameter which makes the pole shifted as compared to knife gravity construction without Weyl symmetry. And we choose this SO1,1 breaking to be a monomial type, and we can realize Higgs pole or PQ pole inflations. So here, previous SO1,1 symmetry is generalized to SO1,n, and n is equal to 4 for the Higgs, n equal to 2 for PQ field. And then this violation of isometry is minimal in the sense that this non-compact isometry is broken down to compact one. And we can still, this compact part of the isometry will be gauged in the standard model. So we need at least unbroken isometry. This is SO n type. So so we understand the form of the Lagrangian potential in particular. We choose the monomial type form of this function f, and this and after choose the gauge for the dilaton, we are getting effective quartic coupling or monomial form for the Higgs field or PQ field. And then in the case of Higgs, SO1,4 symmetry is broken down to SO4, and we have this form of the, I think the usual form of the Higgs potential, and this quartic potential will be dominant during reheating. The equation of state during reheating will be radiation-like. So this radiation-like inflaton energy density must be converted to the usual radiation, and people studied this situation a lot recently. So lastly, we have a Weyl photon with a non-zero mass proportional to this A parameter. A also parameterizing the shift in the pole, and this parameter A controls the tensor to scalar ratio as well as the Weyl photon mass. So therefore, there's a real correlation between the tensor perturbation and the Weyl photon mass. So if you take A equal to 0, this is naive gravity construction. This is the prediction from pole inflation, and A equal to 1 is the Weyl gravity originated Lagrangian, making the tensor to scalar ratio reduced as compared to the naive construction. And here the Weyl photon becomes massive. In our case, we can regard Weyl photon as a dark matter candidate, and we can produce them. Actually, I forgot to say that this Weyl photon, after a certain rescaling of the field, we can show that this Weyl photon is minimally coupled to gravity, so they can produce only by gravity interactions. So called Planck interacting massive particle. In the last 10 years or so, people have been working on in the last 10 years or so, Drunk interacting massive particle. This Weyl photon is one of the dark matter candidates in that context. And the dark matter abundance calculated due to the inflaton scattering or standard model scattering during bleeding or after bleeding. And if you ignore the inflaton scattering contribution, you will have this kind of figure where relic density can be explained in the parameter space for the dark matter mass and the reading temperature. There's a wide parameter space open for the correct relic density if you consider non-inflaton scattering processes. But if you include inflaton scattering process in your game, the inflaton scattering, this is temperature independent. This will dominate in the determination of the abundance, so that we are narrowing kind of down the dark matter mass to be 10 MeV scale. It's a quite of a prediction of our model. 10 MeV dark matter. So I think except this PQ field or action connective Solon one part, I try to explain about the essence of pole inflation in my talk. Okay. Okay, thank you.
Can I have this question?
Yeah, thanks so much for
So
talking.
could you go back to this Lagrangian before you gave fruits with chi's and sigma? Yeah, that one. Yeah. So one thing so you are saying the first line is by invariant by itself, second line is by invariant by itself.
Yes.
Correct? Why do you have to have that A and that A same?
So I explained that I focused on the kinetic term for sigma, and if you add the kinetic term, these two, if you add these two terms, A's are cancelled out. And in the normal derivative terms. And I want to, you can start with the general questions.
But is structure like that going to survive denormalization and all that? That's not going to happen.
Sure, renormalization must be, if this symmetry is exact, then the renormalization of chi and sigma will be the same.
Of course, symmetric, with respect to symmetry,
Yeah.
cancellation of kinetic term
Yeah.
is not because of symmetry.
The cancellation is not a fine tuning, it's a choice of the
Right.
normalization.
I'm asking choice like that classical Lagrangian, of course you can do that.
Yeah.
Of course, once you go around various different scales, such a choice will not survive. It will generate kinetic term.
Yeah, sure. Of course, if you get renormalization, wave function renormalization factor in sigma, you can renormalize sigma. That effect will be included in the form of potential.
But what is the difference between D capital and D small? It's some vector field or what you would say?
So this d mu chi in the end of the day here,
So it's normal vector field.
the round mu minus g
W.
w
And W.
no I.
So it's W mu is just F squared maximum.
No, actually it's about this way. Actually it's about
This one,
basic field for the function.
the field strength kinetic term.
No, but it's expanded there like coupling to the maximum.
It looks like it, but it's not actually.
No Maxwell here, no Maxwell.
This is a different gauge field.
Yeah, this W
That gauge is the
W is the Weyl photon, extra gauge
So
photon.
it's extra massless field or
Recording in progress.
it's extra massless field or you make it also actually like.
It becomes massive.
It
It become
becomes
massive.
massive.
Yes, become massive.
But it's U1 group, right?
Yeah, U1.
U1.
Yes.
Very good. Then why you write this conformal or why symmetry like this on X
It's
mu?
not U1 is a real line.
So they.
It's a, well, as far as biphoton is concerned, it's U1. But the way the biphoton couples to the matter field, it's not phase rotation
That's right.
of the field.
So what is it?
It's a rescaling of the field,
So it's a real line.
the real field.
It's R, not one.
R1.
I1.
Real field remain real. Yes, real line. Okay, real line.
Can it couple to the standard model current? Any current is from the standard model?
It couples to the Higgs field.
It's gazing by transfer.
So this guy, sigma,
Sigma is Higgs.
yeah, you can regard it sigma or the phi I for the Higgs field. You have a coupling, biphoton coupling to the Higgs field.
But so are you considering sigma as a real scalar or complex scalar?
So in this level, sigma is a real field,
Real field.
but you can make it to be complex. There is
But I
no
think
obstruction.
these two are very different because W mu can have a coupling to the current from the complex scalar, but it doesn't couple to the current from the real scalar because there is no such thing in the real scalar case.
So for the complex scalar field,
But
yeah.
sorry, but if W mu has a coupling to the standard model current, that means W mu will decay. Of course, the lifetime can be very, very long.
Yeah, for phenomenological discussion, I think we can discuss more. But here, what I showed is that the Higgs field is completely decoupled after redefinition of the Weyl field. So this W tilde here, W tilde is a linear combination of the original Weyl field and the Weyl current, which is constructed from the dilaton and the Higgs field. And the biphoton coupling to the Higgs field is included in the redefinition of the Weyl gauge field.
But so you can have mass and it's still invariant with respect to this Weyl transformation.
So it's a kind of Stickelberg form of the massive gauge field. Stickelberg gauge field contains dilaton in it.
Stuckelberg adds actually extra field to preserve invariance, which he doesn't need to preserve, yeah, like you want. Here you also do the same thing.
Yes, I'm doing the same thing. I think the only role of this covariant derivative term, these two, those are providing the longitudinal component for the gauge field.
And what does it mean, conformal or wide symmetry? I have never seen such kind of form like x mu goes to exponent alpha x mu, where alpha is a function of the. No, conformal or wide symmetry where you.
This one. Yeah, this is local gauge symmetry, local symmetry.
This is just blaming it instead of metric to the coordinate.
How can you do?
Yeah. This yeah, right.
But is W real or complex? The imaginary.
W real.
So you add the real W to round mu.
It's a real scale symmetry. All the scale symmetry.
But D mu is not then.
No I in D mu.
Hmm?
No I in
No,
D
no,
mu.
Yeah,
here.
that's what
No
I
I,
see.
no I.
I'm just asking whether it's really okay
Yeah.
because that operator will not have definite commutative property. If you round mu is anti-omission, W is omission. So is it okay to do that? I don't know. I mean, I don't have any.
I think
experience.
maybe I haven't thought about that much. I think this this coupling is very peculiar for me. So actually, I wanted to compute the hold-on type ion mixings, the photon mixing with the hypercharge, but I found that contribution vanishes. I think this the form of coupling is very peculiar.
But then finally, you stay with one field or with two fields?
We have a chi dilator and a multiple of them.
And
So by I is I runs over one and number of arbitrary
the
number.
thing is, it
fields.
looks like it's two scalar fields. Because you wrote potential which depends on both of them.
So here, I think that this sigma square can be written as a modulus square.
So
For the
you
multiple-
mean, you mean that effectively it reduced to one scalar. So
Right, effectively the radial distance in
The
the
radial
field space for the multiple fields. So this sigma square is a distance in the multiple fields.
right, very good. But what is the meaning of the second field?
Chi.
Yes.
Chi is a dilator.
Chi is like your Stuckelberg field.
Yes, Stuckelberg field.
But with the help of Stuckelberg field, you can, okay, bring back any symmetry as you want. Right? Because you can take massive photons and you lost U1, then you introduce Stuckelberg, then
I think it's different than usual Stuckelberg because there's a correlation between mass of the photon and the kinetic term for the other sector. So I think
so, but then how you finally leave all the formulas which you calculate for spectral index, etc., just in terms of one field?
yes, one field.
Or second field doesn't enter there.
Second field doesn't second field dilaton
It
fixes.
means that you stay with sigma and with this potential
Yes,
P,
yes,
then W tilde we can forget,
yes.
the last term, and then you are getting back to the tangent hyperbolic potential.
Right.
And this kind of Linde, color, God knows which attractors.
Right.
Which
Alpha
attractors.
characters.
Yeah, okay, good. So it's tangent hyperbolic.
Yeah, sure.
And how you manage to change spectral index because they are mixing it with some kind of quadratic potential, you just changed n there mostly, or you added because of renormalization group this one plus a, or
Here I didn't include locations. So
no, but okay, for ns you wrote formula 1 minus 2 divided by
because
n.
this is the spectral index is the
Correct.
same.
It remains
As in
the same.
it remains the same as in the pole.
So, but the number of folds you increased from 50, 55 to 60, or what happens there? To
Then,
get 9 point,
It's the same prediction as in the Starobinsky
in
or
Starobinsky,
in the
it's
original pole equation.
0.9,
0.966 something. Yeah, 6.5 also.
So, but you can vary n, because then nobody knows, it depends on the reheating mechanism.
Sure. Yeah.
You see, because it can change very easily from 50 to 55.
Yeah.
From
Right.
50 to 60. Therefore, I just don't understand why people make. But for R, anyway, we do not observe it.
Sure. Yeah. Because of this A is unknown.
No, because actually, if you take even this n squared and divide by 12, then for the model which you consider, it's too little. It's still 10 times less than the upper bound.
Right.
You see, upper bound is now 3 or maybe 1% in terms of R, and here you have to have 0.05%, something like this.
Sure. Yeah. I took the A to be positive value because of that.
But
There's always a suppression.
N squared is already more than enough suppression to be in agreement with the convention.
But this is not this point.
It's not his fault, but you don't need
I
it
think
to subtract
the experimental guys must do better to measure those small value of R.
No, actually, people will never get to this value which actually.
It's too small, yeah. But if you take A to be negative value of A, maybe you might. But I don't explore that part. But
Yeah, but 2 divided by n squared is already quite a lot. Because what by itself,
sorry, if A is a negative, sorry, then the biphoton is tachyonic.
but what you will do is this.
So I don't want to
Not
consider
really necessarily. A can be like smaller than -2, then that is not.
A is smaller than minus.
It is
one?
strictly smaller than -1 then.
-1. Okay. There is a parameter space. If A is smaller than -1, there is no pole. Sorry about that.
And what is the special role of Paul? To after bringing this into canonical form, when it's tangent hyperbole, where Paul goes to which place? To infinity?
So yeah, you need to do some exercise. I didn't show
So
the
nice
exact form.
from periodicity.
Yeah, but just to
Because you just take some kind of one interval, one period. At the beginning, you had some kind of periodicity when you were writing the term 1 minus sigma squared in front of the curvature. Now, nothing is left after making rescaling, right?
So when you rewrote all of this, the hyperbolic tangent for the potential,
yes,
that pole is mapped to infinity in this new field.
yes,
So
it's the same
this
thing.
is a device to achieve large, what do you call it? It's large field inflation.
Yeah, large field
One way of,
excursion. Yeah.
we are saying it doesn't have to be a large field if there is a pole.
Yes.
So I mean, I think a few years ago I listened to some talks about bi-gravity, bi-photon, etc. by Dimitri Gilensha and also Yonghyun. And compared to these previous works, what is the new something new and such that
Yeah.
in your
What is new in my work? What is new in my work?
yeah. Because I don't remember what they were talking about in detail. I don't remember. So
Actually, they don't took this.
but the form is familiar now.
Yeah, right. There are many versions of compile by invariant Lagrange, and they rely on Higgs-like inflation. Higgs-like inflation, where inflation is taking place at the large field values.
Yeah.
It's not in the pole.
In your case,
In my case, the pole inflation. So inflation.
They do not consider pole inflation.
No,
in
they
your
don't.
case,
They don't consider. Yeah.
Okay.
Adding two terms also is a common exercise. The first line and second line.
You can do. I can be more general.
I mean, people have played with.
I think myself and Galencia and myself, we did consider more general.
But so then let me ask a question in another way. I mean, biogravity is a kind of dictated by scalar symmetry, right?
Yes.
And everything is fixed.
Mhm.
But in your case, you need some modified form. It's
Right.
not really exactly bi-invariant in the beginning. Pole inflation means. So how do you justify or motivate this specific form of the Lagrange from the symmetry principle?
I think I wanted to claim that the symmetry can be broken spontaneously, and there is a kind of we need explicit violation of the symmetry. So I think that step by step we can introduce symmetry, full symmetry from the beginning, and we know how the symmetry is broken, and we want to keep the necessary part of the symmetry.
This full inflation type is not typical symmetry breaking pattern we are familiar with in the quantum field theory, right?
I think it's similar to the case where the custodial symmetry violation in the standard model, because of loops of the top quarks and the Higgs field.
So maybe we can talk more during the dinner.
Sorry, it's switching on and off.
Are there any more questions?
I have just like a very quick one. So here, like in the middle of your presentation, you showed like expanding the potential up to like a Saxted order.
Yeah.
And then like, and then you're considering like running to a high energy scale.
Yes.
Especially for this number.
Right. Yeah.
But then like the higher order term would also like run, and they're going to be like more larger and larger at a high energy scales.
Mm-hmm.
And is it like truly valid to just like truncate the potential of the Saxted order and not including like octet, for example?
So I think that the only condition that we require is the high order corrections to be smaller than the quartic term, and this also, as discussed, this quartic potential and fixed and higher, even higher terms should come with the suppressed couplings smaller than quartic coupling in unit of Planck scale. You need to suppress. You need to divide this operator by some power of the Planck scale, and we can in that unit we need to bound this high order corrections. It is assumption, of course, but if you start from most general Lagrangian, the sextet coupling to be as small as quartic coupling. That's my assumption. So after the renormalization, but we need to introduce them to cancel the divergences. It's necessary, so it's not renormalized. So I think in this sense, it's not complete. I agree. But what I can say is this running coupling in the reading part could be understood.
With a similarly main question on your next slide, I think. What's running for this delayed quartic running? Maybe I missed it.
Okay. So here, although I didn't show the Lagrangian, this lambda HS is a coupling between Higgs and the singlet scalar field. That also make a shift at the threshold. The running coupling changes because of.
Great. If there are no more questions, let's thank the speaker again.